quality problem appears on the production line. Defect rates suddenly increase, customer complaints begin to rise, and the process team starts searching for an explanation. Traditionally, this investigation might involve a Pareto chart, a fishbone diagram, several meetings, process observations, and many hours analyzing spreadsheets. Now imagine an artificial intelligence system reviewing thousands of process variables in a few seconds. It identifies a strong relationship between the defect rate, a particular machine setting, the temperature inside the facility, and material supplied during a specific period. The system displays a message: probable root cause identified. The answer looks convincing. The calculation is sophisticated, and the pattern would have been extremely difficult for a human analyst to detect. But did artificial intelligence really find the root cause? Or did it simply find a correlation? This distinction is becoming one of the most important challenges in modern operational excellence. Artificial intelligence is transforming root cause analysis. It can reveal patterns hidden inside enormous volumes of data, identify unusual relationships, and help teams investigate problems much faster. But AI can also produce convincing explanations that are incomplete, misleading, or completely wrong. The future of root cause analysis will not belong to artificial intelligence alone. It will belong to organizations that know how to combine algorithmic power, process knowledge, statistical reasoning, and disciplined experimentation. Root cause analysis is one of the most widely used concepts in quality management, but it is also one of the most misunderstood. Many investigations stop at the first reasonable explanation. A machine failed because a component was damaged. A component was damaged because maintenance was delayed. Maintenance was delayed because the schedule was not updated. At this point, the team may declare that the maintenance schedule was the root cause. But why was the schedule not updated? Was information unavailable? Was responsibility unclear? Did production pressure cause preventive maintenance to be postponed? Was the schedule unrealistic from the beginning? Every answer can open another level of investigation. Tools such as the 5 Whys, fishbone diagrams, fault tree analysis, process mapping, and cause and effect matrices help teams organize their thinking. However, the quality of the results still depends on the information available and the questions being asked. Teams may be influenced by personal experience, departmental interests, confirmation bias, or the opinion of the most powerful person in the room. They may focus on the most visible cause instead of the most influential one. Another limitation is the volume of data. A human analyst can examine a reasonable number of variables, but modern processes may generate information from hundreds of sensors, transactions, machines, suppliers, operators, and environmental conditions. Important causes may exist inside interactions that are almost impossible to recognize manually. This is where artificial intelligence begins to change the investigation. Artificial intelligence can process far more information than a traditional improvement team. Machine learning models can compare historical process conditions, detect anomalies, classify defects, analyze images, evaluate text from customer complaints, and identify combinations of variables associated with failures. Consider a production process experiencing surface defects. The available data may include material batches, machine speed, pressure, temperature, humidity, operator, shift, tool condition, maintenance history, and inspection results. A traditional analysis may evaluate each factor separately. An AI model can examine how these variables interact. It may discover that one material batch produces acceptable results under normal humidity, and one machine setting also performs well under normal conditions. However, when that material batch, machine setting, and a particular humidity range occur together, the probability of defects increases sharply. No individual factor explains the failure. The interaction between them does. Artificial intelligence is particularly effective at finding these complex, nonlinear relationships. Can also analyze unstructured data. Maintenance notes, operator comments, customer emails, inspection photographs, and service reports often contain valuable evidence that never appears in a traditional database. Natural language processing can group recurring complaints and identify patterns in written descriptions. Computer vision can compare thousands of images and detect defect characteristics that human inspection may classify inconsistently. AI expands the field of investigation. But expanding the field is not the same as proving the cause. Suppose an AI model discovers that defects increase whenever a particular operator is working. The relationship is statistically strong. Should the company conclude that the operator is causing the problem? Not necessarily. That operator may be assigned to the oldest machine. The operator may work during the shift with the highest production volume. Or the most difficult products may be assigned to that person because of greater experience. The operator is associated with the defects, but may not be responsible for them. This is the danger of confusing correlation with causation. Correlation means that two conditions change together in a measurable way. Causation means that changing one condition produces a change in the other through a credible mechanism. Artificial intelligence is extremely powerful at identifying correlations. Proving causation is much more difficult. An algorithm may discover that production failures increase on days with more maintenance activity. It could incorrectly suggest that maintenance is causing failures. The real explanation may be the opposite. Maintenance activity increases because machines are already showing signs of deterioration. This is known as reverse causality. A third variable may also influence both conditions. High production demand, for example, may increase equipment stress and create more maintenance interventions. A model can calculate associations without fully understanding the process behind them. That is why every AI-generated hypothesis must be examined through process knowledge, temporal sequence, physical logic, and controlled verification. A sophisticated model does not eliminate the need to ask a simple question. How could this factor actually produce the observed effect? The safest way to use artificial intelligence in root cause analysis is to treat it as a hypothesis generation system. AI can tell the team where unusual relationships exist, which variables appear most influential, and which combinations deserve investigation. The improvement team must then translate those findings into testable hypotheses. For example, an AI model may show that defect rates rise when line speed increases, material temperature decreases, and a specific tool approaches the end of its expected life. The team can convert this pattern into a hypothesis. Under lower material temperatures, a worn tool may become unable to maintain the required process condition at higher speeds. Now the team has something that can be investigated. Members can observe the operation, examine the tool, confirm measurement reliability, compare different production periods, and design a controlled test. If changing the tool condition removes the effect while other relevant factors remain stable, the causal argument becomes stronger. If the defect continues, the original hypothesis must be revised. This approach fits naturally into DMAIC. During the measure phase, AI can help organize and evaluate larger datasets. During analyze, it can identify patterns and rank possible causes. During improve, teams can test interventions. During control, models can monitor conditions associated with future risk. AI accelerates learning, but the scientific logic remains. Observe, hypothesize, test, learn, and verify. The objective is not to accept the model's first answer. The objective is to use the model to ask better questions. Artificial intelligence depends on data, and process data is rarely perfect. Sensors may be poorly calibrated. Inspection criteria may change between shifts. Manual records may contain missing values. Operators may classify the same defect in different ways. If the data is unreliable, the model can find patterns that reflect the measurement system instead of the actual process. Imagine that one inspection station reports more defects than all the others. An algorithm may associate those defects with the products, operators, or machines connected to that station. But the real difference may be the inspector's classification standard, the lighting condition, or the resolution of the camera. The AI has found a real pattern in the data, but not a real cause inside the production process. Historical data can also contain organizational bias. If certain failures were investigated more carefully than others, the database will contain more detail about those cases. If employees avoided reporting small problems because they feared consequences, the data will present a distorted version of reality. Before trusting an AI-supported analysis, teams must understand how the data was generated. Is the operational definition of the defect clear? Is the measurement system capable? Are timestamps synchronized? Are important variables missing? Did process conditions change during the period being analyzed? Measurement system analysis remains relevant in the AI era. In fact, it becomes even more important because advanced models can make poor data appear highly credible. Garbage in, garbage out is no longer the complete warning. In the age of AI, garbage in can produce a very persuasive answer out. Reliable root cause analysis requires three different perspectives. The first is algorithmic analysis. Artificial intelligence can search large datasets, detect hidden interactions, and rank possible causes. The second is statistical verification. Control charts, hypothesis tests, regression analysis, designed experiments, and capability studies help determine whether patterns are stable, significant, and reproducible. The third is direct process knowledge. Teams must go to the Gemba, observe the real work, speak with the people involved, and understand conditions that may never appear in the database. These perspectives should not compete. They should correct and strengthen one another. AI may identify an unexpected relationship. Statistics can evaluate its strength and uncertainty. Gemba observation can determine whether the relationship makes physical and operational sense. The sequence can also work in the opposite direction. An experienced operator may notice a subtle change in sound, vibration, material behavior, or workflow. That observation can guide the data team toward variables that were previously ignored. A model can then determine whether the observation appears consistently across historical records. The strongest analysis comes from combining computational scale with human context. Organizations should also document the reasoning behind each conclusion. What evidence supports the suspected cause? What alternative explanations were considered? What test was performed? What happened after the intervention? This creates traceability and prevents algorithmic recommendations from becoming unquestioned authority. Artificial intelligence is redefining root cause analysis, but it is not turning it into an automatic process. It is changing the speed, scale, and depth of the investigation. AI can review more variables than a human team, discover complex interactions, analyze images and text, and identify patterns before a failure becomes obvious. But it cannot guarantee that a correlation represents a cause. It cannot replace reliable measurements, controlled experiments, process observation, or the knowledge of employees who perform the work every day. The most dangerous question an organization can ask is, did AI find the root cause? A better question is, what evidence did AI find? What hypothesis does that evidence support? And how can we verify it? That small change in language protects the organization from false certainty. Artificial intelligence should not be treated as an oracle delivering final answers. It should be treated as an analytical partner that expands human ability to investigate complex systems. The future belongs to teams that can combine AI with Lean Six Sigma discipline. They will use technology to search faster, statistics to evaluate evidence, experiments to test causality, and Gemba knowledge to understand reality. In the next video, we will examine another problem created by the digital age: overprocessing inside modern workflows. Extra reports, duplicated information, unnecessary approvals, and complex systems may look like progress, while quietly consuming time and capacity. Subscribe to the Lean Six Sigma channel and continue with us as we explore operational excellence in the age of artificial intelligence. AI may help you find the pattern, but disciplined investigation is what turns that pattern into a real root cause.